Welcome to Lecture 5.9, Complex Inner Product Spaces. Thus far, we have primarily been dealing with real vector spaces. Things are a little different over the complex numbers, but as we'll see, if we pin down the correct definition of a complex inner product, then basically everything else carries through as before. There's just a slightly different interpretation as to what certain things mean, like the adjoint and orthogonality. But the proofs basically carry through. Let's begin by comparing the notion of what the norm is for real versus complex numbers. For any real number x, its norm, or just the distance it is from 0 on the number line, is written as the absolute value of x. And it might seem a bit silly to write it this way, but bear with me. It's the square root of x squared, which is clearly real. For any complex number z, let's write it as a plus bi, its norm is also the distance from 0, but on the complex plane. Now, it's not right to write this as z equals the square root of z squared. For example, if z equals I, then the norm of I is not equal to the square root of I squared, because that's the square root of -1. But of course, what is the norm of I? It's just 1. It's the distance from I to 1. So how do we define that? Well, here's the right way to do it. It's the square root of z times z bar. That is the square root of a plus bi times a minus bi, and that's just the square root of a squared plus b squared. So remember, the complex plane, if z is a plus bi, then its complex conjugate, z bar, is a minus bi, and angles add and lengths multiply. So if you multiply z times z bar, if this is theta, then this is negative theta. So the angles add, and you will end up getting something on the real line. So this will be z times z bar, and its magnitude, or its norm, is going to be the square of the norm of z, or z bar, and the angle is going to be 0 degrees, and hence real. We just compared R to C. Let's now compare R2 to C2. For any vector x in R2, its norm, or just the distance from the 0 vector, we'll use these double bars, is the square root of the inner product of x with itself, or the square root of x transpose x, or the square root of x1 squared plus x2 squared. In contrast, for any vector z in C2, with entries z1 and z2, let's say z1 is a plus bi and z2 is c plus di, its norm is also defined, it's written the same way with these double bars, as the square root of the inner product of z with itself. However, this inner product, as we'll see, has to be defined a little bit differently. So this is the square root of z bar transpose. That's the conjugate of z transpose times z. And that's the square root of the norm of z1 squared plus the norm of z2 squared. To understand this, I think it's best to compute two examples. We'll start with the norm of the vector 1, 1 in R2. Let's do that right now. So the norm of x here is the square root of the inner product of 1, 1 with 1, 1. And we know how that goes. That's the square root of 1 squared plus 1 squared, which is the square root of 2. In contrast, the norm of this vector z, which is I, let me do that in red, that is also the square root of the inner product of this vector with itself. So I'll write I with I. But notice what happens if we just try to do the standard dot product. So that That would be I squared plus I squared, and that's the square root of negative 2. And that's not real. So that is not what we want. Instead, what we want is take the conjugate transpose. So in other words, the square root of, let me actually write that as well, let me remind you that the complex conjugate of I is negative I. So in the complex plane, if this is I, the complex conjugate is negative I. So that's negative I, the dot product of that, or the inner product with I, and this is 1 plus 1 equals root 2, as it should be. So now here I'm using not just any abstract inner product, I'm using the standard dot product here. And that leads to a definition. If X is a finite dimensional vector space over the complex numbers, then we'll define the complex dot product as follows. So the dot product of Z with W, we will write this as WHZ instead of W transpose Z. WH is just short for the transpose of the complex conjugate of W. And so you literally take the transpose of W and the complex conjugate of each entry and multiply that by the vector Z. Here, H stands for Hermitian. Using the definition of the complex dot product, we naturally get a definition of the norm of a vector Z in Cn. It's easier to define it as the norm squared. So the norm squared of Z is the inner product of Z with itself, which is Z conjugate transpose times Z, which is the product of the row vector Z bar times Z, which is the sum of the norms of the individual entries in Z, Z1 up to Zn. So Z1 squared plus Z2 squared up to Zn squared. Notice how if our vector Z has only real valued entries, then this definition of norm agrees with the definition of norm over a real vector space. So we're not changing the definition, we're just extending the definition when we are in a vector space and our entries don't have to be real but can also be complex. Next, just like how we abstracted the dot product to a real inner product, we can abstract the complex dot product up here to a complex inner product. Here's the formal definition. A complex inner product space is a vector space over C endowed with a map, we'll use brackets for this, from X cross X to the complex numbers, satisfying the following. First of all, it is additive, just like for real inner products. In other words, the inner product of U plus V with W is the inner product of U and W plus the inner product of V and W, and the same thing in the other coordinate. The inner product of U with V plus W is the inner product of U with V plus the inner product of U and W. 2. You could pull out scalars from the first coordinate. So the inner product of KU with V is K times the inner product of U and V. 3. You could pull out scalars from the second coordinate, but you have to put a bar on front. In other words, the inner product of U and KV is K bar times the inner product of U and V. Sometimes this is said to be anti-linear in the second coordinate. There's other terms as well, I forget what they are, but I like anti-linear best. 4. We no longer have symmetry, but we have something close to it. When we swap the order of the entries, we have to take the complex conjugate. In other words, the complex conjugate of V and U, the inner product of V and U, is the inner product of U and V. This is said to be Hermitian. And finally, like for real inner products, we need the condition of being positive definite. So that is the inner product of u with itself is positive if u is non-zero. So notice I didn't explicitly say it's real, but the fact that I'm saying it's bigger than 0 implies that it's positive. The complex numbers are not an ordered field. So these things hold for all, obviously, u, v, and w that are vectors, and all scalars k. Now I do want to say, notice that this is not an alternate definition of a real inner product space. So if we restrict ourselves to vectors where the coefficients are real numbers, and scalars k where these are real numbers, then our definition agrees with the definition of a real inner product space. In other words, if k is real, then this is linear in both coordinates, so it's a bilinear, and it's also symmetric because the complex conjugate of any real number is itself. The first three conditions here are sometimes called sesquilinear, and in Latin that prefix sesqui means 1.5. So I think it's a cute name. It's linear in the first coordinate, and then it's sort of anti or sometimes called semi-linear in the second coordinate. So yeah, 1.5. A map that is of this form, satisfying these first four conditions, is called a symmetric sesquilinear. Sounds like a little bit of an oxymoron because this is not symmetric, but that's what it's called sometimes, or a complex Hermitian form. So in other words, a complex inner product is a complex Hermitian form that is also positive definite. Now that we have defined a complex inner product structure, we naturally get notions such as adjoints and orthogonality like we did in real vector spaces. Let's take a moment to understand what these mean. And it's important to realize that these are not alternative definitions. They are generalizations or extensions of our definitions for real inner product spaces. In other words, if we're in a complex inner product space, but we're looking at vectors that are real, with coefficients that are real, then our definition here should agree with what we had previously. So let's let x and u be complex inner product spaces. For any vectors x and y, the norm of x plus y squared, remember how that's defined, that's the inner product of x plus y with x plus y. So we can use the additivity property to write that as the inner product of x with x, which is just norm of x squared, plus the inner product of x with y, plus the inner product of y with x, and the inner product of y with y, which is the norm of y squared. Now in the real case, this is symmetric, so we could combine this and we could write this as 2 times the inner product of x and y. However, we don't have that when we're in a complex inner product space. Remember that the inner product of y with x is the conjugate, complex conjugate of the inner product of x with y. So now, instead, we have the sum of these two things. And remember what that is in the complex plane. So if we have a vector z, which is a plus bi, and we add it to z bar, which is a minus bi, so z plus z bar is just 2a. So this is z plus z bar, which is 2 times the real part of z. So instead of this being 2 times the inner product of x with y, it's 2 times the real part of the inner product of x with y. And we use this Gothic r to denote the real part. Notice that if we're in a real vector space, or if the inner product of x with y is real anyways, then this just reduces to 2 times the inner product of x plus y. Most results for real vector spaces carry over to complex spaces. And all we have to do is just replace T for transpose with H for Hermitian. For example, the adjoint of a linear map A from X to U is the map A star from U to X, such that the inner product of X with A star U equals the inner product of AX with U for all X in X and U in U. It should come as no surprise that with respect to the complex dot product that we defined earlier, the adjoint of A is its conjugate transpose, that is in matrix form. Now let's just write down why that's true. I should say that this definition I wrote up here is obviously equivalent to just saying X comma AU equals A star X comma U. It doesn't really matter which one of these we use. Basically, we have to put the star, anytime we move the A from the left to the right side or vice versa, we have to put a star on it. So actually, I think this version is slightly easier to verify this, though they're basically the same. Let's just write down X dot AU. This is UHAHX, and if this is equal to A star X dot U, then this is UHA star X. And so for these two things to be equal, the left-hand side and the right-hand side, then it's obvious that AH has to be equal to A star. Now that's if you use this definition here. If you use this first one up here, then I think what you'll get is that you get basically the same thing. You get A star H U H X equals U H A X. So basically here you get that A equals A star H, and if you just apply H to both sides, that's the same thing as saying A H equals A star. So take your pick as to which one of these you like best. The takeaway message is that in matrix form, the adjoint is the conjugate transpose. And once again, this is not a different definition from in the real vector space case. It's just a way to extend it. So if everything is real valued, then you get the transpose as before. One thing you may be wondering is, what if we use a different inner product? So examples that I've done before is, at least for real vector spaces, where the inner product is defined as W. For real spaces, I did W transpose, but let me do WH times some matrix BZ. So we can certainly have a positive definite matrix in here to make things different. And so in this case, the adjoint's not going to be the conjugate transpose. I think it'll be like it'll be a conjugate of the conjugate transpose of A. But I think I will leave that as a homework exercise. Also, we will see later in this class that it doesn't matter which inner product structure we use. If we pick an orthonormal basis, then everything behaves just like the complex dot product. So in other words, given any inner product, we can treat it just like a complex dot product. And so we can treat the adjoint as the conjugate transpose. Let's move on to orthogonality. So the definition is basically the same as in the real case. Two vectors x and y are orthogonal if their inner product is 0. The vectors x1 up to xk are orthonormal if they are pairwise orthogonal and have unit length. So in other words, if the inner product of xi and xj is the Kronecker delta, that is 1 if I and j are the same, and 0 if they are different. So the only difference here is if the vectors x and y have complex entries, you just got to be careful that when you take the inner product, you take the conjugate transpose. Recall that an isometry of a real inner product space that fixes the zero vector is called orthogonal. An isometry of a complex inner product space fixing zero is called unitary. I really don't know why they use different terms for this, especially because we have a notion of orthogonality of vectors in an inner product space, but it is what it is. Since we call a real valued matrix A orthogonal if A transpose A is the identity, we will call a complex valued matrix unitary if AHA is the identity. Basically, the term orthogonal means that the adjoint of a matrix is its inverse in an R vector space, and unitary means the same thing but in a C vector space. Now, this definition of orthogonality, this is not a relation that we really ever care about holding in a complex vector space. So you could definitely write down a matrix where this thing holds in a complex vector space, and that will not have the property that this holds, but we don't really care about that. So we're just going to assume that anytime we're talking about orthogonal matrices, that they are real valued. Here's a quick proposition which we basically established for real vector spaces and orthogonal maps. Go back and watch that lecture. And the proofs carry on almost exactly the same here. Just you have a slightly different meaning as to what A star is. So let U be a unitary map from a vector space to itself. Then U is linear. U star U is the identity. And conversely, U is invertible, and its inverse is an isometry. Finally, we have that the determinant of U is a complex number with norm 1. In other words, it lies on the unit circle. So it's of the form e to the I theta for some theta. Now what we had previously for orthogonal maps is that the determinant of A was plus or minus 1. So that's a special case of being on the unit circle and also being real. So the reason why this one is true is because U star U equals the identity, so the determinant of U star U equals the determinant of U star times the determinant of U equals the determinant of the identity, which is 1. And I guess one thing that I haven't proven, but I will leave as a simple exercise, is to show that the determinant of U star is the complex conjugate of the determinant of U. So you need these things together. So determinant of U is a complex number, e to the I theta, such that it times its conjugate is equal to 1. Finally, the unitary maps form the unitary group, often denoted U of n or U sub n, where n is the dimension. And the special unitary group, SU of n, are those with determinant exactly 1. So we think of those as complex rotations and the other as complex isometries. I'll finish this lecture with an application to Fourier series. Previously in this class, in several different lectures, I've introduced the idea of Fourier series, and this is a way to write a periodic function as an infinite sum of sine and cosine waves. And there I defined an inner product between functions f and g as 1 over pi times negative pi to pi f of x, g of x, dx. Now everything was real valued, so I didn't put a bar on top of g of x because I didn't need to. And with respect to this inner product, if you recall, the cosine functions, cosine of x, cosine of 2x, etc., and the sine function, sine of x, sine of 2x, etc., this infinite set was not only a basis, but an orthonormal basis. That is, if I left out a constant function. Actually, unfortunately, 1 does not have unit length, so 1 over root 2 has unit length. So this is an orthonormal basis, which meant that every periodic function can be represented uniquely as a sum of sine and cosine waves, and possibly a constant. So there's this weird constant out here. I mean, it has to be there, but the fact that it's has to be normalized by root 2 is kind of an artifact of the fact that we are using sines and cosines instead of the much more natural complex exponential. So recall that cosine of nx is e to the I nx plus e to the minus I nx over 2, and sine of nx equals e to the I nx minus e to the minus I nx over 2i. And similarly, you go the other direction by saying e to the I nx is cosine of nx plus I sine of nx. So you could actually go between these two spaces by just turning cosines and sines into exponentials, or vice versa. However, for the inner product to work, you're going to need to put a bar right there. And also, if you do that, if you put a bar here and define it like this, your complex exponentials are not going to actually have unit length. If you want to make them have unit length, you have to divide by 2 pi instead of pi. So let me go through and say that a little bit differently, because if you haven't seen Fourier series before, if you haven't watched my old videos, then what I just talked about probably isn't going to make too much sense. So starting from scratch, we can define an inner product on the space of 2 pi periodic functions as follows. The inner product of f and g is 1 over 2 pi times the integral from negative pi to pi, basically one complete cycle of f of x times g of x bar dx. With respect to this inner product, the following infinite set of complex exponentials, e to the I nx, where n are integers, positive and negative, and 0, which gives you 1. This is an orthonormal basis with respect to this inner product. Therefore, we can write each f of x in this space uniquely as this doubly infinite sum from negative infinity to infinity of Cn I to the n e to the I nx. Now, some people don't like writing this as a double infinite sum, so what you can do is just pull out the constant term, c naught, and then write it as an infinite sum from 1 to infinity of Cn e to the I nx plus c minus n e to the minus I nx. And as before, Cn is just the projection of f onto this unit basis vector, e to the I nx. In other words, the inner product of f with e to the I nx, and that gives us a formula for the Cn's. They are 1 over 2 pi times the integral from negative pi to pi, f of x e to the minus I nx dx, and that minus is because of the complex conjugate. So if you studied Fourier series, you've likely seen these. Maybe you didn't know why there was a negative sign here in the formula for Cn, and this is the reason why. Unless I decide to add another lecture, that brings us to the end of the section on inner product spaces. And what we will do in the next section is look at self-adjoint maps. So these are linear maps such that A star equals A. These are extremely important. They correspond to real symmetric matrices if we're over R, or Hermitian matrices if we are over the complex numbers. And they have a lot of nice properties, like, for example, all of their eigenvalues are real, and there is an orthonormal set of eigenvectors. And from that, we can get a lot of mileage. So stay with us.